Hi. Uh, for a few years, I have been working on this program I call MDL, and I had not posted an update for a while. So today I just released a new version 2.6, that has quite a few new features. And since I had not posted a video for a while, I just wanted to show you some of the new things that you can do with MDL. Uh, in this video, I'm going to very quickly give an introduction to MDL for those of you who do not know it already, just very quickly so that you can see what you can do with it. But then I want to focus on this new feature that is code execution. And basically, the main idea is that MDL can now execute code for you and give you statistics and a set of information from the result of executing code. So the main reason for which I wanted MDL to execute code is that when you write a program, let's say C++ or in Java, typically IDEs have this tool called a profiler, right? And then you run your program in the profiler, and it gives you a lot of statistics, like how many times each function was called. It gives you call trees, how many milliseconds in average does every function take, which is the function that take more time, and all of that. But when writing Z80 code, we do not have such tools. So I wanted to have such tool because I like optimizing code, and if you cannot exactly measure execution time of functions or know exactly which functions are taking all the time, it's actually quite hard to optimize. So I thought that was a missing piece in MDL, and that's what I wanted to add. So version 2.6 already has that, and I'll show you how does it work later. But let's start with a quick introduction to MDL. So what is MDL? MDL is an optimizer for Z80 assembler code that has a bunch of other functionalities, but the core functionality is that you have a program in assembler, let's say a text file or several text files. You give it to MDL, and it gives you suggestions or ways to make it faster or smaller, right? It can give you suggestions, or it can directly edit the assembler for you and just give you the optimized code. But I think suggestions are more useful because then it's up to you which of the suggestions you implement in your code. It can do many other things, as I'll show in a little bit. MDL is open source. It's written in Java. Here's the link, but I'll leave the link in the video description. And why did I build MDL? Well, basically to help use the limited hardware that we have in those classic computers, right, like MSX, Spectrum, Amstrad, etc., that use the Z80 CPU. So the Z80 CPU is quite limited, and if we do not write code that is fast, then our games are going to run very slow, right? So hopefully MDL helps with optimizing a little bit the code that we write. Do not expect like heavy optimizations, but it can give some suggestions that are useful. And also, it's quite, I think it's very useful as a pedagogical tool, so that once it gives you a suggestion, hopefully you learn from that suggestion in the future, and then like you write better code from that point on. And also for fun. So it's actually quite fun to work on MDL. I've learned a lot about optimization. I think I write much better code, much better Z80 code after working on MDL than I did before. So hopefully it can help you too. So, okay, so let's just give a very quick demo with a very simple example of what does MDL do. Okay, so here I have a folder where I've prepared a couple of example assembler files, so you can we can try them with MDL. And here, so MDL is a command line tool, right? So if I wanted to run MDL, I have it here. You can see here the jar file of MDL. So I would just do java.jar, dash jar MDL.jar. And if I just do this, I will get a help screen with a few flags. Of course, MDL can do a lot of things. So if you do dash help, you get all the flags, and there's a lot of flags that MDL has because MDL has a lot of functionality that I've been building over the years. But don't worry, you don't have to know all of those to use it. So let's just start with some basic examples. So let's just open this assembler file. Let's just put it here so we can see it. So this is a very simple assembler function, right? So it's just some code starts here. We have a function that just sets a equal to 0, then b equal to a, returns, and then we set the memory address z000 to a, and that's it, and then infinite loop, right? So this code is not great. For example, there's faster ways to set a equal to 0, and then we set here b equal to a, but b is never used, so, right? So this is actually quite quite wasteful. So we can, if we want to ask MDL for suggestions, we can do java-jar mdl.jar, and then we just say test1.asm. And if we want to use the pattern-based optimizer, we should do -po, and that's it. And then it says, oh, you can replace a, 0 by XOR a. That's right. If we do this is a faster way to make a equal 0. Assuming that the flags are not used, of course, but MDL already knows that. And then it also says that LD b, a is unused, as we already knew, right? So yeah, so we can optimize this part. Interestingly, so this b, a is not used, but if we were to use it, right? So if we do something like this, and then we ask it to optimize again, now it only finds the first optimization because it knows that that b is now used, right? So this is what MDL does, right? It just gives you optimization suggestions. It can do many other things, of course. So for example, if we wanted to actually do the optimizations for us, we can say -asm, and we say test1 optimize assembler, and now it has generated this optimized version, right, where it has already implemented the optimizations, right? It can also, let's say, what it can do. So of course, so I really like this functionality. I use this a lot. Did you do it? Yeah. So what it just did is it generated this little file, this HTML file that has the code, and for every line of code, the bytes that this line of code assembles to, the address, the memory address where every byte goes to, and the position of the binary, the size, the timing, right? How many CPU ticks, t-states, or however you want to measure time, every line takes to execute, right? So this is quite useful. I use this a lot. There's also hyperlinks that link to the function. So if this file grows, you can navigate around the file. I really like this functionality, but let's hide this. Let's see. Of course, it can also generate symbol files, or it can even assemble. So if we just say bin test1.bin, it would generate a binary file. So now it is assembled, right? It's just a binary file with the assembler. So yeah, so that is what MDL does. It can do many other things. But yeah, I just wanted to very quickly introduce MDL. So let's move on to the next thing. So hopefully that was a useful introduction to MDL. So let's now move on to the new feature that I wanted to focus on this video, code execution. And as I was saying before, the main idea is that now MDL can actually execute code. And you would say, why do you want to execute code? Well, so it can be useful for many things. Like, for example, if you have, let's say, a few instructions of assembler, and you want to see what is the effect of executing, you can tell MDL, execute this instruction for me and tell me exactly how the registers or the flags or memory change. So it can do that for you. But the main use is so that you can use it as a profiler, right? So you have a piece of code, like let's say a few functions or even your whole project, and you want to run it through MDL, and you want MDL to produce statistics. Like how much time does every function take to execute, like minimum, average, maximum, how many times does every function get called, and a few other things that I'll show you in a little bit. And as I will always say, if you cannot accurately measure execution time, you cannot accurately optimize code, right? Because I've seen people optimizing code by using these approximate techniques, like changing the border color to see if your code is executing fast or if it's within one frame. The border color is a common technique in MSX, for example, or in Amstrad to measure execution time, but that's very inaccurate. Like sometimes you're optimizing things that when you optimize it, you gain like a few CPU cycles. So you're not going to see that in border color changes, right? So if you want to optimize accurately, you want to measure time accurately, and that's what I'm going for with this code execution feature. So let me just show you with some examples. I'm going to run through a few examples, some very simple ones, and then we'll build up to more complex examples, and hopefully you can see how useful this actually can be. It's been very useful for me, so hopefully it's actually also useful for you. All right, so we are back to the console and folder where I have these example files. So let's just try the execution feature with this very simple file that we just used before for showing MDL. So this is a very simple file, so it might not be very useful here, but just for example, for the sake of an example. So if we want to execute this code, I would do java.jar mdl.jar. I say test1.assembler, and I say execute. And there's lots of different ways to execute, but the simpler one is with this flag e:\u, which means execute until. And until means that you provide a start label and an end label, and it will execute your code from start until it reaches loop, right? And this should be .jar, right? And it produces this that is not very useful, but it basically says the things that have changed, right? A has changed, B has changed, these memory positions have changed. But I can do e.trace, for example, and now it tells me exactly which instructions were executed, right? So it did call function 1, then ld a,0, ld b,a, ret, and then this ld, and then it reached loop and it finished, right? So this is execution. It's not very useful in this particular case, but let me just show you this other test file that I prepared, where you will see that this is much more useful, right? So let me make this a bit bigger so we can see what this test file is. So in this file, I copied a multiplication routine. I don't need this. That was a leftover from a previous example. I have a multiplication routine that I just copied from the internet, right? I just got it from this URL. And I want to see how fast or how slow this multiplication routine is, right? So what I can do is I can do java.jar mdl.jar, and I say test2.assembler this time, execute until. I'm going to execute from start to end. And what I have done here is I have this little test loop that loops for 100 times, and at every time it sets e equal to b, which is basically the loop, right? So in the first iteration, e will be 100, in the next e will be 99, then 98, 97, etc., right? As this loops around. And d will always be 100. And then it will call multiply, and multiply multiplies d times e, right? So it will be 100 times 100, then 99 times 100, 98 times 100, until it does 1 times 100, right? So we do this, and if we just execute this, it doesn't give us very useful information, but now let me, since I don't remember the flags, I'm gonna cheat, and I'm gonna do help, and the flag that we want is this one. So I'm gonna add this flag, and now it has added this additional piece of information here. It tells us the multiply function. It was called 100 times, as we knew, because we looped the loop 100 times. It took 97% of the execution time, of course, because pretty much that's all we do, except for the loop code. And in average, it took 2,643 CPU cycles to execute, and actually not even minimum, average, and maximum. So in this case, it does not depend on the value that we provided. And is that, or probably that's because we did would be there. What happens if we do this? There you go. So basically, the loop in this implementation depends on the value of d, not the value of e. So we're not getting very useful measurements. So if we multiply 100 times the counter, now this function is a bit more efficient. But now we see that the minimum execution time is 69 cycles, the average is 1356, and the maximum 2643. Right? So now we know exactly how long does this function take to execute. And if we do a quick modification, for example, I'm going to put an op here, right? So an op takes 5 t states in an MSX. So if I do this, I should, if everything works well, we should have 5 added to all of these numbers, right? Which is exactly what we see, right? 69 plus 5 is 64. 1356 plus 5 is 1361, etc. Right? So now we have an exact measurement of how long do functions take to execute, and this is actually very, very useful. So let me show you this with an even more complex example, right? But what we could start doing now is we could start optimizing this multiplication routine, or even compare different multiplication routines, right? We could copy here different multiplications routine that we find online and execute them here, and we could see which one is faster and which one is slower, right? And pick the faster one, or even start optimizing this routine here until we get the fastest routine we can find. But I have been using this functionality heavily in my latest project, which is Sheldon Ring, which I have here in this folder. And let me just move to that folder. I have this in MSX, Sheldon, there you go. And let me make sure that I have the right thing. So I'm gonna put this here. Yeah, so now in this profile, basically the command that I was executing, I have it here hard-coded directly in this bash file. So if I do profile, basically it's going to run what we were running before, right? Like remember this execute until that we were using before, and it gives me this. It takes a little while, but because it's executing a lot, some warnings that don't matter, but it now gives me for a lot of functions, right? This is more like a profiler view, right? They are sorted by which one is the one that takes more time. This function was executed 4 times. That took 36% of the execution time. These were the average times, right? It's just giving me the high level functions, but I could, for example, ask for this, and I'll show you in a second what is the difference. And I call profile again. And this thing that I'm going to execute now is what we just did with the first test, but now is going to be with this bigger file. Here I have a list of all the functions in my code base, how many times each one of them was called, what percentage of time did they take, and minimum, average, and maximum execution time of every function, right? So this is super useful. Now you can start optimizing your code like very easily, right? Because now you can start modifying the code. Notice that I'm not even running this on an emulator, right? I'm just running it directly on MDL, and I get this analysis. So I found this extremely useful. So what is exactly that I'm executing here? What I'm doing, let me actually open what I'm executing. So I have this. I'm not executing the whole game, of course, because the whole game relies on this is a game for MSX, and it relies on BIOS functions that MDL knows nothing about, right? Because they are not in my assembler code. The BIOS is not in my assembler code. So I cannot execute the whole thing, but I can execute part of it. And what I have is in my game loop, which is in this file called state play, I have profile. There you go. I have some conditional statement here that if we are profiling, then it does some specific code just to initialize the game. But I have these labels here, profiler start, and I have another one somewhere, profiler end, somewhere profiler end here. So I'm just executing this part of the code, not the whole game, just this part, which is basically the game loop. And what I do is I run the game loop 4 times, right? So it renders the game 4 times, and then it gives me all of this stats. And as I was saying before, a few details, because the game calls BIOS functions that are not defined in my assembler code, but they have to be executed. So when you execute code with MDL, there's this flag for execution ignore. So every time, for example, I'm calling this function or this function or this function, MDL just ignores it and ignores that call, right? So all of the BIOS functions, I'm ignoring them for this analysis, right? So you can ignore pieces of code so that you can execute code that relies on the BIOS. And in this case, it's okay because the only thing that happens is because I'm ignoring those functions, it's just not sending information to the graphics chip. So it would not actually visualize anything, but the main functions are being executed. So I can monitor the code. Something else I can do is, let me see. Yeah, so let's execute this one. So if I provide this flag, e:3, and then I give a number, right? Like for example, 4. I run this again. And what this is doing now is going to give me an execution tree. Oops, I did not save. There you go. So now it's going to give me a call tree, an execution call tree. And up to depth 4, because I set this to 4, but I could have given it deeper, right? So it says that it called this function that was called 4 times, and this function called this one 92 times, and this one called this one 92 times, and this one called this one 1978 times, and this 92 calls took 32% of the execution time, and all of that, right? So you have this nested, basically what you would get with a profiler again, right? So now you can use a profiler with assembler, and I find this very useful. Again, sorry, I'm repeating myself again and again, but I'm just very excited about this functionality. And let me just show you the final thing I wanted to show you, something that is useful for debugging. So imagine I'm writing this function, and I'm actually not sure what is happening. So where did I have it? Here, right? Oops. Oh, because I'm not in the right MDL. Here. Right, exactly. So now we're executing this test2 file. Remember, this is the one with the multiplication. So I want to know which numbers am I multiplying. So I can just do something like MDL watch, and I want to print registers D and E. And now I execute this. Oh, I forgot a flag. Sorry about that. And I had the flag. Had an example of the flag here. There you go. Watch. There you go. There you go. So now you see there's all of this things here. So let's see, I'm going to put multiply, comma. I'll do this again. So yeah, so now we get, it's like doing print statements, right? So we can put print statements while executing. So now when MDL executes, every time it finds this in a comment, it prints whatever you put after it. So basically, it's a comma separated list of either registers or constants. So it prints multiply because it's the string, and then the value of D, the value of E, right? And the value of E should always be 100, exactly. So it's always 100 or 64 in hex. And the value of D should start in 100 and go all the way down to 1, which is what's happening, right? All the way down to 1. So if you have a function that is not working and you want to debug it, so now you can also use this execution functionality to have print statements and debug what is happening. Why is this not working, right? All right, so just to finish up the video, let me just tell you what are my plans for the future for MDL. So what is next? And basically, I have a lot of things in my to-do list for MDL, but one immediate thing that I really want to focus on is on improving the pattern-based optimizer, which is the core of MDL. That was the first optimizer I implemented, and the one that I keep coming back to, even if there's lots of other optimizers now, like I think there's 4 or 5 different optimizers implemented in MDL. The pattern-based optimizer is the one I keep coming back to because it's very fast to execute and it usually gives pretty useful optimizations. So one thing that I keep having troubles with is I add optimization patterns, but it's actually quite hard to manually ensure that those patterns are always correct. So I want to add some formal pattern verification. some functionality so that I can formally verify that all the patterns that are in MDL are always correct. And in that way, you could trust that all the optimizations MDL produce are always correct. So that would be very useful because then you can just rely on it completely blindly, all right? Because right now, even if it's mostly correct, sometimes some patterns, because some bugs or some mistake on my end might be wrong. But if we can formally verify the patterns, then we would be sure that all the optimizations are correct. So I want to do that. The other thing I want to do is sometimes we know that when we execute certain instructions, we know exactly the value of some register, right? Like for example, after a loop, right? Like one of these DJ and Z loops, we know that the value of the register B is always 0, right? Because otherwise we would have loopback. So if we are right after the loop, we know that B is 0. But currently the pattern-based optimizer does not know that, right? There's some patterns that exploit that, but the optimizer does not know that. However, if it could know that, we could define additional patterns to optimize, right? So I want to add tracking of register values. This is already done in the search-based optimizer, and this is key for the search-based optimizer, but I did not bring this functionality to the pattern-based optimizer. And lots of patterns can be added if we had this, right? So hopefully this can expand the set of optimizations that the pattern-based optimizer can do. And then, of course, I want to add more patterns so that we produce even more optimizations. And I also want to add a few more assembler dialects. There's a couple that people have requested that I haven't added yet. Even if MDL already supports many dialects, many assembler dialects, it doesn't support all of them. And some of the ones that it supports, it doesn't fully support them, right? So I want to improve that. And also some additional platforms. Right now, it supports like the standard Z80, as for example, implemented on in a ZX Spectrum, like the variant of the Z80 that is added to an MSX that has all of these weight cycles, right? Which is, so the timings are a bit different from an MSX. It also supports the Z80 that is used in an Amstrad CPC that has all the timings of the instructions completely different. Also the R800 using the MSX Turbo R, but there's a few other Z80 variants that would be interesting to support so that MDL can be used for other for other computers as well that use Z80 derivatives. And yeah, that's it. I hope this video was useful for you. Yeah, and if you have any questions or any requests for MDL, by all means, let me know. Yeah, thanks.